Well, thank you. It's great to be here, and thanks to the organizers for inviting me. So I'm going to talk on joint work with Nate Harmon. And the general goal, yes. The word, oligomorphic. Oligo means few, morphic means shape. It's a group that has finite limiting orbits on something, and that's where the word comes from. Yeah. I guess most people know like oligarchy, which is like rule by the few.
I know the
Yeah, I think Peter Cameron coined the word. Yeah, so the general goal of our work is to construct and hopefully classify tensor categories. And I'm going to talk about this part, the construct part. And I think Nate's talking next, and I think he's going to talk about this classify part. All right, so our work starts with Lean's category rep_st. So I just want to review a little bit about how that category works. All right, so I'm going to write this S for the symmetric group. All right, so we have the finite symmetric group, Sn, and this acts on an n-element set, which I'm going to call omega n. And we can linearize this to get the permutation representation. And I'll just work over the complex number. So this is just the n-dimensional representation of Sn. And I guess the basic idea of this category is that the tensor powers of this representation behave in a uniform way within. And so let me say two precise things in that direction. So first, if we look at maps between tensor powers, so Sn maps from, let's say, A tensor power to B tensor power. So this is just a vector space. And this vector space stabilizes when n gets large and A and B are fixed. And this is not hard to see, but I'll explain a little later kind of exactly how this works. And it's not just like the dimensions stabilize, but there are kind of compatible bases as n varies. And the second observation is that so these Hom spaces are stabilizing, and sort of the composition laws also sort of stabilize. It's a little more subtle here. Maybe stabilize is the wrong word, but they behave in a nice way as n varies. So if we look at composition, so we have the A and B tensor powers, and then let's say the B and C tensor powers. And so we can compose to get a map from A tensor power to C tensor power. And so if A, B, and C are fixed and n is large, like then these vector spaces all have like sort of the same basis as n varies. And so you can ask, what are the structure constants for this map? How do they behave with n? And they behave as polynomial functions of n. And again, this is in the regime where A, B, and C are fixed and n is getting large. OK, so we can use these two observations to build a category. And this is this category, rep_st. OK, so here T is a complex number. And this whole thing is basically just a formal symbol, just a name. And really, this construction is going to be in two stages. So first, we consider the following category. So the objects are just going to be formal symbols. V tensor n, where here n is a natural number. And then the Hom spaces are going to be these stable Hom spaces. So Hom from this to this is stable Sn Hom space. And for composition, we use this polynomial composition law, and we just substitute in t into the polynomial. Okay, and this is a category. And then this category is I'm going to take the additive and Karoubi envelopes of this preliminary category. So the additive envelope just means we're going to be considering formal direct sums of these symbols, and then the Karoubi envelope is adjoining like images of idempotents. Okay, so this is a C-linear additive category, and it has a tensor product on objects that works in the obvious way. And well, you'd have to say quite a bit more to justify why it's actually a tensor category from the way I've defined things, but it is. Okay, so here's maybe the main thing to know about this category. This is mostly due to Deligne, and some part of it is due to Kalms and Ostrich. Yeah, that's right. That's right. So yeah, my natural habit is when I say tensor category, I just mean like an additive category with a symmetric monoidal structure. And I'll use the word pre-Tannakian for abelian category, finite length, all that stuff. Okay. So first of all, yeah. So if t is not a natural number, this is like the generic case where things behave in a simple way, then rep st is a semi-simple pre-Tannakian category. So in particular, it's abelian in this case. All right, so at t, when t is a natural number, it's more complicated. In this case, this category is not abelian. But Deligne constructed a closely related abelian category. And Kalms and Ostrich proved that it's the abelian envelope in a certain technical sense. So I'll just say rep st admits an abelian envelope, which I think is often denoted this way, just with an ab superscript. And this is a non-semi-simple pre-Tannakian category. And then finally, let me just mention that none of these categories have moderate growth. So all these categories have super exponential growth. And so roughly, if you, maybe I shouldn't write too low, if you look at the length of the nth tensor power of the sort of basic object, this is going to grow roughly like exponential of n log n. So if you remember on the first day, Kevin was talking about these tensor categories of moderate growth, and that's where the length was always like an exponential function of n. And that's the setting where like this Deligne theorem applied and where you automatically had fiber functors or super fiber functors, and this is outside of that case. Okay. Any questions so far? All right, so this is like kind of the starting point for us. So this category rep st, like it's a very pretty object, but this construction that I gave you, I think is, well, I don't really like it because it's a very formal construction. You're kind of building this category by hand, and a very natural object should have like a more meaningful construction. And that was basically the first goal of this project with Nate. We just wanted to like construct rep st in a nicer way. So let me tell you how our construction works just in this case. And our first idea is that this category should be associated to the infinite symmetric group. So just as notation, I'm just going to write S for the infinite symmetric group, and you can do whatever version you want, really. You can do all bijections of n, but I'll just take this finite-ary version. And this acts on omega, which is just this set. Yes.
These kind of stabilizations of cells, I think it also happens when you have like other spectrum multiplicity structures. If you can like build do all of this with other like just like grow the first row, but have more things below the first row.
I think those will just all be in this category when we take the Kubi envelope.
Oh, okay.
Yeah. All right, so why are we doing the infinite symmetric group? Well, it sort of makes sense from this point of view because we're saying that this space stabilizes as n gets large, right? So like when you go to infinity, it should just be the natural thing. And so I want to explain that in a little more detail. So first, let me make just kind of a very simple observation. If x and y are finite G sets, where here G is any group, and we look at the G maps between the two permutation modules, so Cx is a vector space with basis x, Cy is a vector space with basis y. When we're looking at linear maps between vector spaces with bases, these are just matrices, right? So giving a linear map like this is giving a y by x matrix. And if we want it to be a map of G modules, it has to be a G invariant matrix. So these are G invariant y by x matrices. And so to be perfectly clear, by a y by x matrix, I mean just a function from this set to the complex numbers. That's just recording the matrix entries. And this is a G set, and so by G invariant, I just mean this function is G invariant, which means if you want, you can just regard it as a function on the quotient set. And so let's go back and now look at this Hom space from that point of view. All right, so this V, so remember, Vn is the linearization of just omega n. And so if I take its 8th tensor power, this is going to be the linearization of just the 8th power of this set. You just do the Cartesian product of omega n with itself 8 times. And so by what we said here, this is going to be Sn invariant omega n to the b times omega n to the a matrices. Okay, and if you think about the Sn orbits on this set, that set actually stabilizes as n goes to infinity, and it gives you the value at infinity. So the Sn orbits on this are the same as the S orbits on here for n large. Okay, and so this gives us like a description of the mapping spaces in the Deligne category. So in rep ST, we can now say that Hom between like these basic objects are just given by these matrices. So S invariant omega b times omega a matrices. Okay, so this is like maybe the first key observation, because now we have like a description of the Hom spaces in this category that's like a little more natural. It's not like depending on any auxiliary n. But this is kind of the easy step, like describing the stable Hom spaces. We now need to say how composition works, and that's more interesting because that's where this parameter comes in. So essentially, we need to like say, how do you multiply these kinds of matrices? These are going to be, omega is an infinite set, right? So these are really infinite matrices, and there's supposed to be some rule for how you multiply them. Okay, but before we get there, let's just think about where this parameter t is really coming from the S infinity point of view. So t is the categorical dimension of the basic object. And that like corresponds to the fact that if you look at the basic representation of Sn, that has dimension n. And why does this have dimension n? Well, that's because we're linearizing an n-element set. And why does this set have dimension n? Well, This is a transitive Sn set. The stabilizer is Sn minus 1. So this is really looking at the index of Sn minus 1 in Sn. And so this t over here is really telling us like the index of S infinity minus 1 in S infinity. That's like how I want to see this t kind of group theoretically in terms of S infinity. So to say this, let me introduce a little more notation. So I'm going to write S parenthesis n for the stabilizer of these points in S. I mean the pointwise stabilizer. So it's the subgroup of the symmetric group that fixes each of these numbers. Right, and so what I'm saying here is that I want to say that like the index here is equal to t. And let me put that in quotes because it's obviously not literally true. Okay, and you can keep going and figure out what other indices should be. So if you think about the second tensor power of v, that has dimension t squared. But v splits off as a sum end from that, like the diagonal. And so what's left over has dimension t squared minus t. And that's giving you the index of S2. And then you can sort of maybe guess from these things that like the index of S2 and S1, well, we should just divide. So this should be like t minus 1. But you can already see that there might be a subtlety here if t is 0. Like maybe this shouldn't be considered valid. OK, so this is getting like very wishy-washy now because we don't have any formal definitions. So let me like make a definition to make this kind of idea rigorous. And this definition here is really like one of the key ideas kind of our work that leads to everything. So I'm going to define for you what's called what we call a generalized index on the infinite symmetric group. And so far we've been working over the complex numbers, but in this definition I want to make it work for a general ring. So this is going to be on S valued in a ring K. So this is just a ring, commutative ring. So this is a rule that assigns to every containment of open subgroups U inside V, or let me say V inside U, a number which I'm going to denote this way. So I'm going to use this like power series bracket type thing as notation. And this should live in K. And there's some axioms, but before I say the axioms, let me say what this word open here means. So U is open if it contains one of these basic subgroups Sn. Okay. So whenever you have like a permutation group, you get an induced topology on the group where you take stabilizers as elements to be the basic open sets. So S infinity is naturally a topological group in this way. And you can see that like we should only be thinking about open subgroups here because by thinking about like small tensor powers, we're just going to see like SNs, and we're not going to get to like much smaller groups than that. Okay, so this is the data, and now there's some axioms that I have to write down. Okay, so such that all right, so the first three are very obvious. The index of a group in itself is 1. We should have conjugation invariance. And then we should have like transitivity. So if we have open subgroups like this, then we get this familiar rule for the index. And then the last one is a little less obvious. So if I have two subgroups contained in U, what I can do is so to motivate this axiom, let's think about the quotient space. So I can think about, let me write U mod W. So the index is supposed to sort of be the cardinality of this set, right? And I can think of this as a V set and decompose it into orbits under V. And so this decomposes, well, this is isomorphic to. Yeah, so to do this decomposition, I want to do the double coset decomposition for U under V and W. So if I write U as a disjoint union like this, then this will be isomorphic to this. I might be getting an inverse in the wrong place, but this is basically what it is. And I guess it's important to note here that we're in an infinite group, but it's true that the double cosets here, the set of them is always finite. To see that, you just have to think about the double cosets of Sn and Sm inside of S, and it's easy to see that that's finite. OK, so basically, we just want to say that like the cardinality of this set should be the same as the cardinality of that set, and that's going to give us this identity on indices. So the index like this should be the sum of these indices. OK, and that's the definition.
Does it make sense to consider indices a non-convoluted ring?
Yeah, it does. Because like this kind of presentation kind of things are in the correct order or whatever. There's like a, yeah. But it turns out that ring is commutative. Like it sort of forces commutativity. The axioms do.
For this particular group, but for other groups?
Yeah, in general. Yeah. Nate and I actually have a comment in our paper that you can like do this non-commutative version, and Deline sent me an email. I was like, no, it's always commutative. OK, so I want to tell you like what are all the generalized indices on the infinite symmetric group. Right? This is really nice now because we have like this group in this precise definition. It's a really natural idea. So what are they? It's a very natural question. And to answer that question, it's convenient to note that there's actually like a universal one. So let me explain that. So there exists a universal generalized index with values in some ring. And we call this ring theta, capital theta. OK, and by universal, I mean that giving a generalized index with values in K is going to be the same thing as giving a ring homomorphism from theta to K. And the definition of this ring theta is really easy. You just take formal symbols like this for every V inside of U, and then you quotient by this idea. OK? So if we want to say what all generalized indices are in all rings, we just have to compute this one ring, theta of S. And so the answer is that this is the ring of additive polynomials. So this is like the subring of the polynomial ring over the rational numbers spanned by binomial coefficients. Maybe one way to describe it. OK, so in characteristic 0, if we're just looking at homomorphisms to like the complex numbers, this is saying that generalized indices, there's a one-parameter family. Like you basically say what this index is, and once you know that this is T, all other indices are determined. And they're just going to be these kind of natural guesses.
So why is it called additive? I thought it was integer value.
Oh, that's what I mean. That's what I mean. Thank you. Yeah. Right, so in characteristic 0, one parameter family, but it's more interesting in characteristic P. And the fact that we get integer valued polynomials here instead of just like the polynomial ring, it's really important and connects to interesting things about tensor categories and positive characteristic. But I'm not really going to get into any of that in this talk. OK, so the point I want to make, though, is that we have this idea of generalized index, and the generalized indices are like the parameter space for them is matching up with the parameter space for the Deligne categories, right? There's one parameter in each case. And so I want to explain now how you can go like directly from having a generalized index to like building a nice construction of the Deligne category. And there's going to be one auxiliary thing that we have to do first.
So can you comment why you said this, the Deligne comment, that this ring is always commutative? So why is that, roughly?
So it's this universal ring is always commutative.
Yeah.
I don't remember exactly. I mean, it's very easy, but it's just like using these properties.
Okay.
Yeah, you can just deduce commutativity. Yeah. OK, yeah. So before we do composition in the Deligne category, I want to tell you how you can make a general theory of integration based on having a generalized index. So let's fix a generalized index valued in K. And now if X, let's say X is in a set with an S action, so an S set, and I'm going to assume that there's finite limiting orbits and that the action is smooth, meaning that the stabilizers are all open. And so basically, whenever I say S set, I'm going to always make these assumptions on it. So we're going to define this space of functions on X, which Nate and I call Schwartz space. And this is just going to be the functions, well, I can say smooth functions, phi from X to K. And here, smooth just means that the stabilizer is open. So the stabilizer of phi in S is open. OK, and these are the functions that we're going to be able to integrate. So I want to explain to you how we make the integral of phi. So suppose we have some Schwartz function. So by definition, there exists some open subgroup that stabilizes it. And we're going to look at the orbit decomposition of X under U. And so again, it's one of these basic, I mean, the fact that there's finite limiting orbits is a special fact about the infinite symmetric group. So phi is constant on each one of these xi's. So phi restricted to xi is some constant, let's say ai and k. And xi itself, this is a U set, so I can write it as like U mod vi for some subgroup of U. And so now the definition is that the integral of phi of x is just going to be the sum of ai times this index. OK, so let me just show it, maybe the simplest example. So if we take our set X to just be this omega, like the basic set that the symmetric group acts on, so omega looks like 1, 2, 3, like this. And so a function on X, on omega, is just assigning a number to each one of these points. And this smoothness condition just means that once you go far enough out, you get the same number. OK, so if phi is in here, then we can say that like phi of I is ai, so a1, a2, a3, and so on. And smooth means that ai is equal to some fixed thing, let's say a infinity, for I greater than equal to n. So there exists n such that this happens. OK, so basically we have like n random values, and then the same value from there on. And the integral is going to be the sum of those like random values. And then what's left over, we put the stable value, and we then put the volume of this set, which is t minus n. The whole set has size t, so when we remove n elements, it has size t minus n. OK, and this theory of integration works very well. If you have a map between S sets, you can do push forwards, and it behaves in the expected way, like you have a transitivity law for push forwards, and like every kind of natural thing you would want works. It's very nice. And so we can now use this theory of integration to say how we multiply matrices. So let's say that X, Y, and Z are S sets, and we have two matrices. So A is going to be a Y times X matrix. So meaning a function from Y times X to our base ring K. And I'm going to assume it's smooth, and B is a Z times Y matrix. So both are smooth. So we want to define their product, and this should be a Z times X matrix. And we just use the usual formula for matrix multiplication. So I have to tell you the value at Z comma X, and we just integrate over Y and do this. Okay? So now let me directly construct a category for you. So we're going to define a category. It's called perm of S. And it depends on our generalized index. And I'm just going to use the symbol mu for that. So if you look in our paper, we define these things called measures for the group G. And measures are equivalent to generalized indices. And so we always work with measures and use the symbol mu to denote a measure. But measures are a little more technical, so in the talk I just wanted to not mention them. But that's why we have this kind of funny notation now. So so we define this category. So the objects are still going to be formal symbols. I'm going to call them vec sub x, where here x is an S set. The mapping spaces, so let me just write HOM from vec x to vec y. These are going to be S invariant y times x matrices. And then the composition law is matrix multiplication, as defined here. And this category is additive and has a tensor structure. And this kind of, the intuition here is that this is supposed to be like a category of permutation modules. And vec x is like the linearization of the set X. And addition and multiplication work just like they normally do for permutation modules. So if I direct sum these, I just get the permutation module in the disjoint union set. And if I tensor them, I get the permutation module in the product set. OK, so this is like a nice direct definition just in terms of this generalized index. And I guess I'll just state as a fact that so this category is additive, but it's not Karoubian. But if we take the Karoubian envelope of this over the complex numbers, we get back the Deligne category. So this is in the case where our field is C.
So this story is a bit reminiscent of motivic integration.
Yeah, maybe.
Some more precise connection, maybe for other class of groups.
I don't know. I've sort of thought about that kind of thing, but yeah, I haven't figured anything out. So this is basically recovering this sort of non-abelian version of the category. There's also a nice way that we have to write down the abelian version, which is a really, I think, beautiful thing. But I don't really have time to go into it. But I just maybe want to say one word about how this works. So I'm just going to call this a remark, because there's going to be a lot of details missing here. So we can define this ring, which we call A of S. And this is going to be the inverse limit of these short spaces on these quotient spaces as we shrink the open subgroup U. And the idea is that this is supposed to be sort of like functions on the group. I mean, it's not literally that, but that's what you should think. And so this is sort of like a group algebra, and we call this the smooth group algebra. And this definition of integration actually does let you define a multiplication on this by kind of a convolution. So it is a associative unital ring. And we show that this abelian version, you can identify this with the category of what we call smooth modules over this ring.
So really the algebra depends on the index?
It depends on the generalized index, that's right, yeah.
This comes with a tensor product?
Yeah, so there's a way to tensor these modules, and it really has meaning. It's not like now some formal thing. There's a mapping property. Like we actually have modules over a ring, and there's some mapping property. It's essentially some kind of topological completion of the algebraic tensor product.
For this last line here, is there some specific choice of mu, or are you saying that?
Mu corresponds to T.
Oh, okay,
Yeah.
for that choice.
Yeah. Okay, so this is basically the story for the symmetric group. Any questions before I move on?
So can you change the field over there instead of complex numbers?
I mean, over characteristic 0, everything's the same, and in characteristic P, things get a little bit weird. I mean, you still have this definition, but like this category of smooth modules over this ring is not the right thing in characteristic P. Well, it's just kind of like the Deligne category in characteristic P, but a version where like you use all Young subgroups and not just, yeah, it kind of has more permutation modules than maybe the naive definition.
Is it easy in this picture to see why it's semi-simple when T is like not an integer? Or?
Well, we have a general theorem which implies that, which I'll say in a minute. So let me move on and now say how this works for general groups. So the great thing about this approach to the category is you can just change the infinite symmetric group to another group and everything basically works. So that we need to like identify what we were using about the infinite symmetric group in this story. And of course, we were using the topology all over the place. And the most interesting thing we used about the topology was that we had these finiteness results in several places about like double coset spaces. So let me introduce this class of groups where everything works. So we say that a topological group G is admissible if it's Hausdorff, non-Archimedean. This just means that the open subgroups define the topology. And then the interesting condition is what's called Roekel precompact. And this just means that these double coset spaces are finite.
But non-Archimedes is the same as totally disconnected.
I'm not sure. OK, so I'll tell you in a minute how to make examples of these things. But for the moment, let's just say that we have this kind of group. Yeah, so all I want to say is that like everything works. So for admissible G, we can define this notion of generalized index. Like just the exact definition I wrote for the symmetric group works. And the key point is that in this fourth axiom, the one that had addition, there you needed these double cosets to be finite. And that's where this Roekel precompact condition is figuring in. We can define this universal ring that carries the universal generalized index. And computing this ring theta of G, this is a really important problem, like for specific examples. It's really cool. Like you pick your group G, and then you have this problem of like computing this really natural ring, and it's very hard. And you can define this category perm G mu, if mu here is a generalized index.
So if you have an algebraic group of periodic integers, is it an example of this?
I don't think so. No.
What is not?
You're doing G of ZP?
GLN over ZP.
Oh, GLN ZP. Yeah, that's profinite. So profinite groups works. Yeah. But GLN QP doesn't work. Yeah.
And what is this ring? Is it like ring of
GLN ZP? I don't know. I'll tell you what happens for. Well, sorry. For any profinite group, this is just Z. Yeah, like the only way to define an index is to use the usual one. Yeah. All right, so let me say one theorem, and I'm not even going to precisely state it, but I want to at least give you an idea of what we can prove. So definition, a generalized index, we call it regular if whenever you look at the index of something in G, this is a unit of your ring. You can just take K to be a field if you want. There's really no loss there. And then we're just asking that these indices be non-zero. And we say it's quasi-regular if there exists some open subgroup, let's say H inside of G, such that the restriction to H is regular. So such that this is in K star for all open U and H. All right, so here's a theorem.
Are you going to say for RFC? Which other?
Yeah, let me do that in a minute. Yeah, but I'll tell you that. So here's a general theorem. So if mu is quasi-regular and satisfies this condition that we call property P, which I'm not going to tell you what it means, but it basically means that you can reduce things modulo sufficiently many prime numbers. So like, it means the generalized index should be valued in a subring of K, where you can reduce things. So if the generalized index is Z valued, that's OK. But if it's like Q valued and like actually Q valued and not like living in some subring, that would not be OK.
What is sufficiently many prime numbers? Infinitely many prime numbers?
Yeah, so like you need to be able to like say if a ring element is 0 by reducing it to characteristic, positive characteristic. OK, so if this happens, then this perm category has an abelian envelope. And you can define this using modules over the smooth group algebra. And moreover, if mu is regular, then it's semi-simple.
Is it both ways?
I think so, yeah.
The RevST category you started with
Yeah.
at the beginning was defined as like this sort of using the tower of Sn.
Yes.
Do you have a similar thing happening here where you have like towers of open, which can define like you could define the same RevST as you did using like limits and expecting?
Not really. So these groups don't have to be related to any finite groups. So like S infinity is kind of like the union of the SNs, and that's where that picture is coming from.
Yeah.
But a general admissible group will not have any finite groups really.
Do you have other examples which come from such towers, which you can realize such an equivalence?
Yeah, so like there's all these examples of like Deligne interpolations of families of finite groups, and Knopp worked out kind of the general picture here, and all those will fit into this picture.
Okay, and they will be equivalent to the perm here.
Yeah, this kind of everything works the same. But the really interesting thing about our work is that there's examples that don't come from that.
Yeah, sure.
Yeah.
And
Yeah.
just another question. When you have morphisms between two groups, can you relate like the thetas of the two different
Not
groups?
for most morphisms, like maybe for surjections you can, but not just for a continuous homomorphism.
But also this ring can be 0, right?
Yes, yes. Although we only recently did Nate and Ilya figure out the first example where that happens. Yeah. OK, so let me make one more general comment, which is like, where do we get examples of these admissible topological groups? This is where we finally say the word oligomorphic in the last 5 minutes of the talk. So definition, a permutation group, so G is the group, it acts on a set omega, is oligomorphic if G has finitely many orbits on all powers. And like I said, if you have any permutation group that induces a topology on G, where you use stabilizers here as open subgroups, and if you start with an oligomorphic group, you'll get an admissible topological group. And roughly speaking, a general admissible group is sort of like an inverse limit of oligomorphic groups. They're basically pro-oligomorphic. All right, so in the last few minutes, I want to give you some examples. All right, so the basic example, of course, is the infinite symmetric group acting on this set. And here, so we've already talked about what the generalized indices look like and what the theta ring looks like. So if we're over the complex numbers, there's two cases. If the parameter belongs to the natural numbers, this is like the bad case, then the measure is, so mu is quasi-regular in this case, and not regular. But it does satisfy property P. And so our general theorems recover the fact that there's an abelian envelope. So we kind of reprove Combs and Ostrich theorem. And if T is not an N, then mu is actually regular and also satisfies P. And so we recover the semi-simplicity. OK, so 2, we can look at GL infinity over a finite field acting on FQ infinity. So that's an oligomorphic action. So first question, whenever you have an oligomorphic group, is what is the theta ring? And in this case, Nate and I computed this. And these computations are like not easy, at least by our methods. Like we do everything by hand, and you have to like figure out what all the open subgroups are and how they work. And it's really a mess. So it'd be very nice if anyone could figure out better methods for computing. But the answer is that this is a Q analog of the ring of additive polynomials. I keep saying additive, integer-valued polynomials. So like they should be integer-valued on like Q integers, basically. And so again, so in characteristic 0, this ring just becomes one variable polynomial ring. The only difference is where this, in positive characteristic, it's a little weird, but in characteristic 0, there's just one parameter. And there's, again, two cases. Let's say we're in characteristic 0. So the kind of bad values, in the way that we do it, is when T is a Q integer. So in this case, the measure corresponding to T, or the index corresponding to T, is quasi-regular and not regular. And it does satisfy P. And so our general theory gives an abelian envelope. I should say that the perm category, like this not abelian version, that was constructed by Knapp. That was one of his examples. And he didn't prove this theorem in that case. So at the singular values, he could not construct the abelian envelope. But our theory recovers that. And when T is not a Q integer, this is like the generic situation, mu is regular, which means we sort of expect semi-simplicity. But we can't prove if it satisfies P. This like looks like it basically comes down to the Artin primitive root conjecture, which is kind of weird. Artin's primitive root conjecture. I mean, we need something like that. You know, like if you have an integer and you look mod P, when is it a primitive root? Yeah, that kind of thing. Because we need to know that like kind of integrality of Q polynomials evaluated at things. But anyway, so it probably satisfies P, but we can't prove that. So our theory can't actually prove semi-simplicity here yet, but Knapp had already proved that. So we know that it's semi-simple. So P is a question mark.
So can you prove this Artin conjecture?
No.
Or just prove?
And I should say that Thorsten, who's speaking this afternoon, and Enna also have results like this. So we'll hear more there. So I guess I'm about out of time, but let me say one new example, because these two examples I said were like already known. So we can take G to be the automorphism group of the real numbers that preserves the total order. And this acts on the real numbers. And that action is oligomorphic. And if you think about, so like the way that you get an open subgroup is by taking a stabilizer. So if we take like 0 and 1, and we take U to be the stabilizer of them, if we look at like G mod U, this will be like the set of ordered pairs A, B in R squared, such that A is less than B. And that's a smooth manifold. And U mod V always has the structure of a smooth manifold. And you can define a generalized index by taking its compactly supported Euler characteristic. I mean, these are never very interesting smooth manifolds, but this is the formula. And this defines a generalized index. It always takes values plus or minus 1, so it's regular over any coefficient field. And it's taking values in Z, so it satisfies this property P. And so this so this leads to a semi-simple pre-Tannakian category over any field with super exponential growth. And this was the first example of such a category in positive characteristic, where we actually have semi-simplicity and super exponential growth. And we call this category the Delanoy category. And Noah's going to talk on this category. Like his whole talk is going to be about this category. And he's talking after Nate. And so in this example, the theta ring is actually z to the fourth. So there's really 4 measures, and I just told you what one of them was. The other 3 are not quasi-regular. And these perm categories still exist. And it looks like they should have abelian envelopes, like nilpotents have trace 0. We know that. But we cannot construct the abelian envelopes. And this seems like a very hard problem. So yeah, there's a bunch more examples. But yeah, I'm out of time, so I'll stop there.